Okay, thank you. So first I should thank the organizers for inviting me here to speak. It's an honor to be here speaking at Amplitudes and especially at the IAS. Today I'm going to talk about some work I've been doing in the last few years on computing scattering amplitudes for Kerr black holes. And it's in collaboration with these authors here, and two of whom are at the conference here, so Henrik and Paolo. So I'm pretty lucky that I'm speaking after two great talks by Sri and Stefano, so I probably don't have to motivate so much why I'm interested in studying scattering amplitudes for Kerr black holes. Only to say that there's there's been a lot of success using scattering amplitude techniques for modeling black holes and computing gravitational observables for black hole scattering. The only point is that as soon as you want to now describe an object that's spinning, then there's some complications that enter. You now have an extra scale in the problem, and you have to think about how your extra spin degrees of freedom are coupling to gravity now. So if you look at the type of, your scattering amplitudes are essentially building blocks when you're computing your classical observables. And these scattering amplitudes are going to depend on the Wilson coefficients in your effective theory. So of course, if you just want to describe the scattering of a generic spinning compact object, then that's fine. You can just keep these Wilson coefficients free. Of course, that means you'll probably only be able to work at like finite orders in spin because you can't work with infinitely many unfixed parameters. But what's I found interesting, and what's I guess interesting in general, is what about if we look at a very specific source, and in particular a Kerr black hole? So this is a very beautiful solution, very simple. It's characterized by mass and spin. And one would expect that the effective theories, the scattering amplitudes corresponding to Kerr black holes, are particularly simple, exhibit some symmetries and some potentially better behavior. So at 3-point, the linear and Riemann-Wilson coefficients have been fixed. You can do it straight from those 3-point amplitudes, from the linearized energy momentum for Kerr. This exponential form was first written by Vines. But the quadratic and Riemann in general for generic spin haven't been fixed. They first start to contribute at spin to the 4, and I think so far in the literature they've been fixed up to spin to the 5. So we can try to fix them in two ways. But if you just want to think about the classical physics, then you can try fix them, or they have been tried to be fixed in multiple ways. The first is you can try to fix them at all orders by positing some classical symmetry that should govern these Wilson coefficients, and that was done. This like spin shift symmetry was posited, and the benefit of this is that you get these results that are all orders in spin. Alternatively, you can really do like a proper GR calculation, let's say, so solve the Tucholsky equation and fix the Wilson coefficients from there. That means, though, that you'll be working at finite orders in spin, and there are still numerous open questions here, which I'll discuss a bit later, but a bit to do with conservative physics versus dissipative, and some non-analyticity, and whether we should be incorporating them or not. But in this talk, so just to say that it's not exactly clear how to fix these Wilson coefficients, at least to all orders in spin, from a purely classical approach. Instead, you can decide to study a quantum effective theory for the Kerr black holes, and that's mostly inspired by the fact that in, 2017, 2018, there was this relation between these pretty nice 3-point amplitudes between two massive spinning particles in a graviton, and which was related, essentially once you write it in new variables, you find that it encodes exactly the same information as the linearized energy momentum for Kerr. So you see this exponential structure again. So this arrow here, it's really what, I guess, ultimately like these steps here, you expand in a new basis, a basis of spin operators, and then you go to the classical regime. These 3-point amplitudes were written, like for separate reasons, just to do with the spinor, essentially how simple the spin-elasticity structure was. So they were written without a Lagrangian. But we know that for spins up to 2, that they are in fact the 3-point amplitudes corresponding to minimally coupled massive spinning fields up to spin 2. But once you go beyond spin 2, there's not really there's not really a well-established sense of minimal coupling, at least at the level of the Lagrangian, in the sense that you can't have fundamental massive fields with spins greater than 2 when you're coupling to gravity. So there's some sort of breakdown happening here at spin greater than 2. But maybe, we're at an Amplitudes conference, maybe you say you don't care about the Lagrangian, let's just use some on-shell recursion techniques. And indeed it was done. And you can just pick, okay, if you're in one helicity sector where they have the same helicities, that works, and you have a perfectly sensible candidate amplitude at 4 points. But if you go to the opposite helicity sector, you see again that there's a breakdown, and particularly a breakdown again at spins greater than 2, because if you just naively do a BCFW or like using notarity cuts, you generate this spurious pole. Well, a spurious pole that starts to contribute exactly when S is greater than 2. So something is happening when S is greater than 2. And as I said, that also corresponds to when you're actually considering interactions of higher spin particles with gravity. So what's the approach we take? So the goal of, I guess, this talk is to present a proposal for this quantum amplitude, which won't suffer from these problems here. We're going to present a quantum amplitude, and we'll also present a classical amplitude. And we'll start by constructing a quantum effective theory that which generates these 3-point amplitudes. And this is where we'll discuss some higher spin constraints. And then from there, we'll be able to propose some consistent 4-point amplitudes for generic spin scattering. We'll also have to introduce some classical constraints here. And then finally, the classical amplitude would just define it to be the classical limit of the quantum amplitude. So we never ansatz anything at the level of the classical physics. Everything is done at the level of the quantum amplitude. And then as long as we understand what this limit is, which is why there's a little asterisk, because we'll discuss it in a little bit, then we'll be able to generate a consistent classical amplitude. And that would be the input to any of the classical observables you want to compute. And yeah, to note, this will be in all orders in spin, and we'll find that it has some pretty nice matching to parts of the solution of the Tucholsky equation. So let's get started. So we want to study higher spin theories. So we need to, let's look at what the free theory will be. We choose to work with a tower of symmetric double traceless fields. So it means for a spin S field, we need S+1 fields that go from a spin S all the way down to a scalar. They're going to be related by a tower of massive gauge symmetries. And this is necessary so that we always have 2 S+1 degrees of freedom, right? The physical degrees of freedom of a spin S field. And here we write our free Lagrangian. It's potentially a bit messy. You have all these here. This line here is all diagonal interactions, but we have lots of off-diagonal kinetic terms in this part here. Great. So now we want to add interactions. So we'll couple to gravity. But as soon as you couple to gravity, you'll break the gauge symmetry. So the Lagrangian will no longer be invariant. And what does that mean? It means actually that you're going to end up propagating in physical modes. You no longer have 2 S+1 degrees of freedom propagating. And to fix that, we'll add some non-minimal interactions. And these non-minimal interactions we need to fix them, right? We're going to add them with free parameters, and we need to cook up some constraints or consider some constraints that will fix these free parameters. And those constraints will be, among other things, some higher spin constraints. Sorry, these are higher spin constraints. There'll be Ward identities, some power counting. The power counting is actually that we'll just consider up to an upper bound of the derivatives in the cubic interactions, and a current constraint. And I'll discuss them shortly. Let's just emphasize, though, the full cubic vertex has, I guess you can think of it as having 2 contributions. You have a contribution from the minimally coupled kinetic, like the free Lagrangian, and then you have the non-minimal vertex, right, where this is where all the free parameters are. So the Ward identity comes from, essentially, it's a repackaging of the massive gauge symmetry, but instead of having to work at the level of the full Lagrangian, now we can work at the level of currents. So in principle, we take these 2 legs on shell, and then we'll essentially just vary this one off-shell leg here. And the Ward identity ends up being an identity between 3 currents, where the off-shell leg is differs in spin by up to 2 units. So this is one of the constraints that we're imposing. And the second constraint that we have is the current constraint. And this is related to imposing better high energy behavior, so softer high energy behavior, is related to like tree level unitarity. And in fact, if we were actually considering massless fields, you would find that this constraint here is quite similar to the massless ward identities. It's essentially just the derivative of the current. Great. So having discussed our constraints, maybe we can discuss the results. So at 3 points, that means that those constraints are enough in gravity to uniquely fix the 3-point amplitudes to be exactly those 3-point amplitudes which are relevant for Kerr. So it means we found the constraints, we found the theories that generate these Kerr 3-point amplitudes. Now, if we upgrade some of our constraints to be quartic order, so we use a cubic EFT, and then we also use some extra quartic constraints, then we'll also find some constraints on these additional contact terms that appear in the 4-point amplitude. And at least in gravity, we find it, okay, for spins less than 3, that we can't add more contact terms. We also consider a gauge theory, which we call root Kerr. Root Kerr has many different interpretations in the literature. Here, what I mean by root Kerr is the theory that at cubic order reproduces these 3-point amplitudes, which are related to gravity by a very simple double copy. And then beyond cubic order, there is the theory that essentially is fixed by the same constraints as the Kerr theory. So that's maybe a bit different to how other people would interpret root Kerr. Now, there's still some freedom, right? Once we're beyond spin 2, we still have some freedom, but it's much like a smaller parameter space than if you were just allowing yourself to add any contact term to the 4-point amplitude. So we will need additional constraints. Great. Before I present the 4-point amplitudes, I'm going to present the effective Lagrangians. But in order to do that, I'm actually going to use a slightly different formulation of higher spin, of like interacting higher spins, because it's more compact. So instead of using a tower of symmetric double traceless fields, I'll use instead a single chiral field and couple it to gravity or electromagnetism. And the benefit of this is it's much more compact. You don't have this higher tower of fields, but it's describing the same theory. So even though it says chiral, and indeed minimal coupling breaks parity, we can cure it order by order in the interactions by adding non-minimal interactions. So this line here, this is the Lagrangian that generates the 3-point amplitudes originally written in this 2017 paper for the gauge theory, and this is the gravity 3-point amplitude Lagrangian. And if we want to go to quartic order, then of course we're going to need to add some curvature squared corrections. So let's present the quantum amplitudes. We'll start with root Kerr, so the gauge theory. And let's point out some key points, some key properties. So notably, all the spin dependence is encoded in these polynomials, right? So what I mean by that is, okay, everything that's sensitive to whether I'm scattering a spin 1 or a spin 2 or a spin 3, that's all encoded in these polynomials here, which we find are actually these symmetric homogeneous polynomials. And I'll discuss them a little bit more and as to why they're a particularly nice basis for the amplitude. The abelian gauge theory amplitude has a contact term, like a special contact term, like identified. And that's actually there in order to be consistent with the non-abelian amplitudes, because we do the full non-abelian treatment. And this contact term is generated essentially by Clauss-Kaif relations. Great. The amplitude matches the literature up to spin 3/2. So that means up to spin 1 for the BCFW amplitudes where there's no spurious poles, and then up to spin 3/2 for an amplitude presented by some of the authors in another paper. And then indeed, we still have this freedom in the contact terms. And once I present the Kerr one, we're going to proceed to try fix those contact terms. Right. So now we'll do the Kerr amplitude, and we'll find that it's got very similar structure. Okay, the poles has the extra massless pole and is potentially slightly more complicated, but many of the same features, all the spin dependencies in the polynomials, it matches, that's a typo, that should be 2. It matches the amplitudes I presented at the beginning, which were computed from BCFW. It matches them up to spin 2, where there's still no spurious pole. And then at spin 5½ it matches an amplitude that was previously written in the literature as well. So let's quickly discuss these polynomials, or highlight them at least. So I've written them in a form that doesn't really make it clear that it's polynomial, but this is like one of the most compact ways to write the polynomials, but there's a more obvious writing otherwise. And these seem to naturally arise from the Cairo-Lagrangian either way. So this term here is essentially what the vertex corresponding to the non-minimal interaction in the Kerr-Lagrangian is. And we find that it's really just on the nose one of these polynomials. And so after identifying these polynomials, noting that they are a particularly nice basis for our amplitudes, we'll now construct all all the free contact terms to be in a basis of these polynomials. So while we identify that all the pole terms seem to be well described by these polynomials, so we'll choose our contact terms to be written in terms of these polynomials as well, and then we'll fix any free parameters in front of them using some classical constraints. Okay, so in order to discuss classical constraints, we need to maybe highlight some subtleties in the classical limit, because again, the idea is that we're going to use classical constraints to fix quantum contact terms. So we need to make sure we are doing this limit pretty consistently, so that we don't, so that it's consistent. And something that's interesting to ask is, okay, can I work at finite spin and get classical amplitudes from that? And that was potentially motivated by, posited by Vadia, let's say, where it was suggested that the scattering of spin S particles, you should get up to the 2S classical multiples. And that seems to work for special cases, in particular for 3-point amplitudes for root Kerr and Kerr. And it works because these coefficients, when you expand the quantum amplitude in the spin operator basis, are not spin dependent. So you can read off the classical amplitude multiples directly. But that's not a general statement. In fact, we can find an example. So the 3-point scattering, the scattering of 3 leading register states of the open string. And all you have to do is compare the spin 2 scattering and spin 3 scattering, and you see straight away that the quadrupole is extremely sensitive to whether you are scattering spin 2 or spin 3, which you'd expect generically to hold anyway. And indeed, you see that for the generic spin, you have this complicated spin dependence. So the question is really, how can you consistently read off a classical multiple at finite spin when you have like a dependence on the quantum number? So instead, what we do is we consider a large spin limit. So that's where we scale our quantum number with an inverse power of h bar. And just some motivations for this is that, in this limit, now your expectation values of the operators, the variation vanishes, so you then behave more classically. And ultimately, these are what you want to identify with the classical spin parameter. So that's already good news. And now we also have well-defined classical multiples. So if we go back to the example of the quadrupole for the leading register states, in the spin to infinity limit, you get a 1/4, and I put a tick, and maybe you have no idea why that would be the correct answer. But in this paper, we compared it to the classical configuration of a rotating rod, which is what you expect for leading register states. And we indeed find that this is the correct classical multiple. So the large spin limit is a very consistent way to take classical limits. Alternatively, you can also do the coherent spin limit, and this is where you scatter coherent states. And that also works very well. But I will just note again that you don't get away from the fact that you need this infinite spin information. You do need to do this resummation all the way to infinite spin. And both of the two, so large spin and coherent spin, are equivalent. So you can do either or, and they have strengths, and they have different strengths. Before I present the classical amplitudes, let's just discuss the variables quickly. We have, some pretty standard variables, and then maybe I'll just highlight the Z variable here, which is dependent on the modulus of the ring radius, or the spin parameter. And this is a pretty special variable. We see that it shows up in our amplitudes, particularly in the dissipative sectors, because it's, let's say, sensitive to, well, it's not parity invariant, let's say, or maybe it doesn't respect time reversal. So we'll find that anything that's dissipative in the amplitude will be odd in Z. And then also this W parameter is encoding the spurious pole, essentially, of this BCFW amplitude if you took the limit of this. So we can't have anything higher order than to the order of 4, I guess, W to the 4 in gravity for this. I'll just highlight again these polynomials. So maybe with the current spins limit, you're concerned that we have this infinite spin sun, maybe it's going to be complicated, but as soon as you have these polynomials in your amplitude, actually you get these extremely nice entire functions spat out by the current state. And it also means that your classical amplitudes are actually going to generate infinite towers of spin multiples, right? So a contact term that's like written in terms of these polynomials will generate infinitely many classical multiples. So you gain a lot. You just have to make sure they're correct. Good, so let's present. I'll maybe rush a little bit on the root Kerr because it's potentially a bit less interesting, but if you just take the 4-point amplitude that we had previously, we have the highest spins constraints, and we'll just add 2 classical constraints. So we'll just require that it's finite in the classical limit and that this quadrupole is fixed by the spin 1 scattering. Then that the second constraint is essentially fixing this delta. Then we have a single resulting contact term of this type, and our classical amplitude is just written in terms of some hyperbolic functions, basically. Now, let's go to Kerr, because we have maybe more to say. So likewise, for Kerr, we can take our 4-point amplitude, we constrained it with the highest spin constraints, and we'll just add one more constraint, and that constraint is that we want to fix the a to the 4 multiple by comparing to the scattering of fixed spin 2 states. And so that's one constraint, and it will fix one parameter in the contact terms, and we'll generate, I guess this is our quantum contact term that will be fixed by these constraints. And it will introduce this term to the amplitude. So we have a proposal for a Kerr, classical Kerr amplitude, computational amplitude. Let's compare it to what there is in the literature. So let's compare it to solutions of the Tucholsky equation. And so in 2022, there was this nice paper where they computed an amplitude up to a to the 7 comparing to Tucholsky solutions. And I'll just mention that this solution here had 2 bookkeeping variables. One, which was eta, which was tagging terms sensitive to boundary conditions. So whether you had incoming waves or outgoing waves, there was a sign flip. And also alpha, which was just tagging terms generated by expansions of polygamma functions. So if we compare the amplitude I just presented on the previous slide to this Tucholsky solution, we find there's an exact match up to a to the 7 if we send eta and alpha to 0. So that means we're reproducing all the terms that are not tagged, right? And that there are terms. Okay, well, maybe we can do a bit better. Let's actually try reproduce the eta terms, so these terms sensitive to the boundary conditions. And we can do that just by using one piece of information. So let's just use the eta up to a to the 5 coefficient. And we can use that to fix a coefficient in the ansatz. And we just have to modify our contact term that we added previously to have this like eta dependence here. And maybe you should complain a bit, because actually now I've added a contact term that doesn't respect the symmetries of the quantum amplitude anymore. So because of this sign flip in front of the eta, actually this amplitude would no longer satisfy a swap of legs 1 and 2, which you would usually expect. But that's exactly because we're adding something dissipative to the quantum amplitude, which in the way we've set up our theory, it's not, let's say, yeah, it's not probably not the best way to do it, but we can do it if we close our eyes. And what we find is that now we have an enhanced matching. We match everything except like everything, including eta terms, up to, but not these alpha terms anymore. So you can ask, okay, what about these alpha terms? We can match them in the sense that we can construct contact terms that will match these alpha terms, but we don't have predictive power in the same sense that we had them before. But I think it's fair to say that there's still some questions here about what these alpha terms really are and whether they're defined, like whether there's like an invariant meaning for them or whether they can be absorbed. Maybe we can talk about it a bit in the discussion. But yeah, so just a summary of the results so far, and then maybe I'll be able to discuss quickly some upcoming work. But so what have we done? So we constructed some consistent higher spin theories for the Kerr and the gauge theory equivalent. we presented some proposal for the quantum competent amplitudes for generic spins, right? So now the spins could go arbitrarily high and there would be no spurious poles. We studied this classical limit with spin, which was pretty important for imposing our constraints. And as a result, we got these really nice classical all order and spin competent amplitudes for both the Kerr and the root Kerr. And unfortunately for root Kerr, we don't have so much to match to, but for Kerr, we can compare to the Tucholsky solution. And as I said, we match up to a to the 7. We're compatible with a to the 8, and we can predict further, at least in this alpha 0 sector. Right, and by compatible with a to the 8, what I mean is there was a more recent paper by Bautista and let's say Zihan and some other authors, I have them cited maybe on the last page. We're compatible, but in the sense here, they don't have this tagged parameter alpha anymore. So because they've done like a near zone, far zone splitting, and I think it's fair to say that whilst we're compatible, it would mean we would have to add an additional contact term. I think it's still unclear to me, at least, whether this far zone, near zone splitting is like, I guess, has a unique splitting. So I don't think I'll have time to talk about work in progress, but I'll say that just quickly that we're currently, what we have now with classical amplitude started to look at what these quadratic agreement operators are in a wordline EFT. And I would just say that for now, we see that we need them, they're non-zero, and in fact, we need infinitely many if we want infinitely many orders in spin. And it doesn't seem like there's a super nice structure, but that's even the case for the same helicity amplitude, right? So even these nice same helicity amplitudes seem to need a lot of, need these Wilson coefficients. Okay, I think I'm almost out of time. I'll just maybe flash Outlook. So as I said, there's definitely still a lot to consider in terms of how to understand near zone and far zone effects, whether we should be incorporating only far zone in our amplitudes or if we want to model everything. There's maybe more to say in terms of incorporating non-conservative effects. There's definitely, I would agree that just adding the contact term is potentially not the most consistent way to do it. Maybe we should be studying EFTs where you allow multiple physical spins to interact. Yeah, something I didn't mention so much is that our amplitude is actually only really valid in the super extremal limit for spin. So there's definitely more to understand there. Maybe I'll leave it at that. Thank you.
Yeah. So we're good with time. Are there questions? Yes, Uli.
Thanks for a great talk. You just said this quickly, but for the spinning case, this curvature squared spin to the n, you said that they're non-zero, but aren't these the static love numbers that people have computed and claim that they're all zero? What's the deal?
I would say, okay, I'm probably not the expert on this at all. I would say it's not clear to me that they are the static love numbers. And I would say that for sure, it seems like we need them. So even if you just want to, even if you want to ignore the opposite helicity amplitude and just take the same helicity amplitude as a given, then we do seem to need them. Yeah. So I think it's maybe not so correct to call them the static love numbers, but potentially we can talk about them.
Okay, thanks.
Thanks for a very nice talk. Actually, one comment and one question. So for the S to infinity, one of the reasons we want to go to S to infinity is because we have this so-called Casimir degeneracies, where that's basically the reason why when Mao Zedong and friends did this 3PM calculation using spin 1 particle, they couldn't get one coefficient which Gustav and friends were able to get. And the question I have is for the Compton amplitude. So you have this expression, kind of closed form expression for it. And it seems to have a lot of spurious poles. Can you actually rewrite it in a form that doesn't have any spurious poles? Because we already have like master integrals where you can just put it in and get the one loop coefficients.
Right. So maybe just to be clear, this is not even a spurious pole because W and Z actually like have a P dot Q pup like defined inside them. So this is definitely not something to worry about. Maybe you can worry about the functions. So these, they don't have spurious poles in the sense that they're not how to say. Okay, so something we are working on is seeing whether we can just plug in these amplitudes without expanding order by order in spin. You can just expand this order by order in spin and it's a polynomial. So if you want to just go like order by order in spin and plug things in, then you can do that. You just turn the crank and you go series. You just do a series expansion.
Well, I was more of thinking like, can we express it in terms of linear sums of exponential functions?
I don't know if there's a closed form without this denominator.
Okay, thanks.
I think you would just series.
Yeah, we can talk about it later.
Yeah.
So it looks like there are no more questions. Let's thank Lucile again.